Welcome to EDU World Space.
For this problem, we will consider the two scenarios. The first being the initial scenario when the strings are still intact and the balls are rotating about point O. The second scenario, which will be the final scenario, is when the strings break and the balls move off freely. So using these two cases, let's first apply the conservation of momentum. To be more specific, the conservation of linear momentum. So what this tells us is that the momentum before the break must be the momentum after the break. So the initial momentum is 3m, the mass of the three balls, times the velocity of the mass center, v bar. And this must be equal to the momentum of the system after, which is the momentum of A, mva, plus the momentum of ball V, mvb, plus the momentum of C, mvc. So we can rewrite this as 3m times the initial speed v naught in the I direction. We want to find v naught I in part A, and this is equal to m into 3.5 feet per second v A in the j direction minus m vb also in the j direction plus m into 6 feet per second in the I direction. So if we equate the coefficients, the I and j coefficients, we get that 3. So the one vector equation gives us two scalar equations. 3v naught is equal to 6 feet per second. And the j components tell us that 0 must equal to 3.5 feet per second minus the speed vb. So from here, we can see that obviously vb is equal to 3.5 feet per second. That's the speed of ball B. And as required, our answer for part A, the initial speed, or let's find the initial velocity of the ring v naught is equal to 2 feet per second, which is the speed, and this moves horizontally to the right. So vector v naught is 2 feet per second to the right. So vb is equal to 3.5 feet per second. We'll call this equation 1. So we know the speed of ball B. Now, the next thing we'll do is use the conservation of angular momentum. So we've used the conservation of linear momentum. Now we'll use the conservation of angular momentum about the origin, about point O. So initially, before the break of the strings, we'll call this angular momentum about point O HO naught, the initial angular momentum. And this is simply, remember, angular momentum is defined as the position vector crossed with the momentum vector, or the position times the momentum. And this is 3m, which is the mass, times L squared times theta dot. So L theta dot gives us v, our velocity. mv is the momentum and L is the position. So that is our angular momentum before the break. Now to apply the conservation principle, we have to look at the angular momentum after the break. So after the break, our angular momentum is simply HO, about point O. And this is equal to minus m VA XA plus m VA into XA plus 16 by 12 plus M VC into 9 by 12. So that's the momenta times the positions for particle A, particle B, and particle C. And if we substitute our values into this equation, we get this to be M into 3.5 times 16 over 12 plus M into 6 times 9 over 12. So we get, after the break, the angular momentum about the origin is equal to the mass M of one ball times 9.1667. So conservation of angular momentum tells us that the angular momentum after the break must equal to the initial angular momentum before the break. HO is equal to HO naught. And so we equate these two expressions and we get that 3m L squared theta dot is equal to M into 9.1667. And so this implies that L squared theta dot is equal to 3.0556. So we have an expression with two unknowns. We have two unknowns which we wish to solve for, L and theta. So we'll call this equation 2. Now let's apply another conservation theorem, the conservation of energy. So we've applied previously the conservation of linear and angular momentum. Now we'll apply the conservation of energy. So initially, before the break, we have energy, kinetic energy T naught, and T naught is equal to a half times the total mass of the system, 3m, times the speed of the center, v bar squared, plus 3 times the individual contributions from each ball, a half m v prime squared. And so this simplifies as 3 over 2 m v naught squared plus 3 over 2 m, and v prime squared is L theta dot all squared. And so substituting values into this, we get 3 over 2 times m times 2 squared plus 3 over 2 m L squared theta dot squared. So that's our kinetic energy before the strings break. After the break, we have kinetic energy T. So our final kinetic energy T is equal to a half m VA squared plus a half m VB squared plus a half m VC squared. And this is equal to a half m into, substitute the values we have, 3.5 squared plus 6 squared, and this is equal to a half m into 60.5. So now we have our energy, our kinetic energy before the break, and our kinetic energy after the break. So conservation of energy tells us that T must equal to T naught. The final energy must equal the initial energy. So a half m into 60.5 must equal to the initial energy 3 over 2m times 2 squared plus 3 over 2m L squared theta dot squared. And so if we rearrange this, we can divide both sides by m. We are left with L squared theta dot squared is equal to 16.167. And we'll call this equation 3. So if we take equation 3 and divide it by equation 2, we are left with theta dot is equal to 16.167 over 3.0556, and we get theta dot to be 5.2909. And then since we have theta dot, we can use equation 2, and we find that L squared is equal to 3.0556 over 5.2909. And hence we get L squared, or we get L, the length of the string, to be 0.75994 feet. So hence we have actually solved for B and C. And so B, the length of the string L, is equal to 0.76 feet. And for part C, the rate of rotation of the balls is calculated by theta dot d theta dt, and this is 5.29 radians per second.